At the end of this video, you will learn the concept of diffraction grating and you are able to solve problems regarding diffraction grating. Okay, let's start. Diffraction grating. It is a tool that divided the light into separate wavelengths. This is the concept on how the light divided by diffraction grating. We have here a laser, a diffraction grating. There are many slits inside that, and a screen, whatever it is, or maybe a cloth or a paper or even a side of the wall. Take note, when you want to do this concept or this experiment, you need to go to a dark room in order to see the divided light clearly. When we turn on the laser here, the light passes through multiple slits or the diffraction grating, and the different intensity of the light divided into separate wavelengths. Okay, let's draw it. The light passes through diffraction grating. The different intensity will be divided. When we look closer to it, this is what happens. There are multiple slits here inside the diffraction grating, and the light, the different intensity of light will be divided into separate wavelengths. Okay, M is the grating order integer. We have here M is 0 and M here is 1. Then the highest grating integer, okay, we have here -1 and M -2. D here is the grating constant line or the distance between each slits, and it is equally placed or it is equally divided. And we have here the angle of incidence of light, which is our theta 1 and theta 2, and our wavelength lambda. And for additional, the distance between the grating and the screen is L, and the lines per millimeter, or we have here N, is the lines per meter here. The main formula we are going to use is that d sine theta is equal to m lambda. We finished the concept of diffraction grating, or on how the light is divided into separate wavelength. Okay, let's move on to some calculation. Okay, we have here problem number 1. A diffraction grating has 5,000 lines per centimeter. Calculate the second order angle if a wavelength of 650 nanometer is used as a light source. Okay, we have the formula d sine theta is equal to m lambda. and D is equal to 1 over N. The lines per meter, N. But first, we have to convert 5,000 lines per centimeter to lines per meter. Okay, 5,000 lines per centimeter to 100 centimeter. Because 1 meter is equal to 100 centimeter. We have to cancel centimeter here, centimeter here. Okay, 5,000 times 100 is equal to 5,000 times 100 is equal to 500,000, or 5 times 10 raised to 5, because 5 0 here is 5. 1 2 3 4 5 lines per meter, and we will use the formula here. D is equal to 1 over N, equals to 1 divided by 5 times 10 raised to 5, okay, equals 1, okay, 1 divided by 5 times 10 raised to 5 equals 2 times 10 raised to negative 6 lines per meter. And that's our distance between each slits inside diffraction grating. Okay, we have to calculate the angle of incidence of light. We have the D here, and we will only input the value. Okay, we have but first we need to find theta 2, and our wavelength is 650 nanometer. Okay, and the second order integer is 2, because it is second order. Okay, we have to input the value. Okay, our D is 2 times 10 raised to negative 6, and sine theta 2 is equal to M is 2, and our wavelength is 650 times 10 raised to negative 9. You are wondering why there's negative 9 here. It's because the nano means 9, milli is negative 3, micro negative 6, and nano negative 9, and so on and so forth. Okay, we have to plug in 2 times 10 raised to negative 6 2 times 650 times 10 raised to negative 9, 1.3 times 10 raised to negative 6. Okay, we will divided 2 times 10 raised to negative 6. Cancel. Divided 2 times 10 raised to 6. Okay. Sine theta. And we have to divide it. 1.3 times 10 raised to negative 6. Divide by 2 times 10 raised to negative 6 is 0.65. That's our sine theta 2. Okay. And theta 2 is equal to sine negative 1. Or 0. Sine 0.65 is 40. And our theta 2 is 40.5 degree. That's our incidence of light. Okay, let's move on to our second problem. A diffraction grating has 10,000 lines per centimeter. If the third order bright fringe has an angle of 25 degrees, what is the wavelength of the light source? And just like what we did earlier, we have to convert 10,000 lines per centimeter to lines per meter. Okay, we have to cancel it. And $10,000 times 100 is equal to 1 million. Okay, we have 1 times 10. We have 6 0. Okay, 6 lines per meter. And we have to convert it. 1 over n is equal to 1 divided by 1 times 10 raised to 6. 1 times 10 raised to negative 6 meter per line, or lines per meter. Okay, we have the D. Okay, we have to find the wavelength of the light source, or the lambda. Our theta 3 is equal to 25 degree, and m is 3. That's third order. That's 3. Okay, we have to input all the sine theta is equal to m lambda. Okay, our D is 1 times 10 raised to 6, and sine our theta 3 is 25 degree equals 3. M is 3, and our wavelength lambda equals, we have to input all the data here. 1 times 10 raised to negative 6. Wait, I forgot the parenthesis. 1 times 10 raised to negative 6, parenthesis, sine, parenthesis, our theta 3 is 25 degree Okay. Equals 4.2. 0.23 times 10 raised to negative 7. We have to divide 3. Divide by 3 is equal to 1.41 times 10. Times 10 raised to negative 7 meter. Okay. Divide by 1. We have to convert it to nanometer. Times 1 nanometer is equal to 1 times 10 raised to negative 9 meter. Cancel. Then 1.41 times 10 raised to negative 7 divided by 1 times 10 raised to negative 9. Okay, 141 equals to 141 nanometer. That's our wavelength of the source. Okay, that's it. Thank you for watching.